So now we're going to begin a discussion of acid-base titrations. This is going to build upon our prior knowledge of reaction stoichiometry. So we're going to see those mol-to-mol conversion factors and our molarities come together in this section. So a little bit of background before we jump into the actual word problems. First off, you're going to see the term equivalence point quite a bit. And the equivalence point is simply when you're mixing an acid and a base and the moles of acid equal the moles of base. So equal, and then you have the beginning of equal in there, right? Equivalent. So that's what an equivalence point is. How do we see that in the lab? You can absolutely use a pH meter. However, when there's not enough pH meters to go around, and to be honest, the process with a pH meter is a little bit more tedious. So a lot of chemists will use what's known as an indicator. And that's a dye that changes color around a certain pH. So like other dyes, like food coloring, you only need to put a couple drops into your solution when you're doing your titration. Phenolphthalein, that's the most common indicator in the undergraduate laboratories. And it's pretty common, just in research and stuff too, because it changes color around a pH of 7. And why is that important? Well, the pH of 7 is neutral. So what I drew here was a pH scale. I drew it from 0 to 14, even though I have seen with our stronger acids like hydrochloric acid, pH values that are negative. So it doesn't actually stop at 0, but anyways, between 0 and 7, your solution is considered acidic. And if you have this phenolphthalein indicator in an acidic solution, you're not even going to know it. It's going to look clear. And as you're titrating, you add more and more base. You're going to add it drop by drop by drop. And all of a sudden, you're going to see it turn either light pink or dark pink. So if you get a very, very nice light pink color, and I'm going to put a picture of that after I'm done talking. If you get this very nice light pink color, you know you've reached your equivalence point. You've achieved that point where the moles of acid equals the moles of base. Neutral, well, water is neutral, just to give us an example of something that's neutral. In terms of acidic, things like lemon juice are acidic. Battery acid, any of your acids as well, right? On the basic side, that's going to be between 7 and 14. So if you throw some of that indicator into any kind of cleaner, a drain cleaner or bleach, that's going to turn hot pink. So many of your cleaners, soap, are basic in nature, and oftentimes you could identify something as being basic because it's going to feel slippery. Think soap. The basic items are very slippery. And so when you're doing a titration, the goal is that light pink color. You don't want to go too far and get into the hot pink range. That means you've added too much base during your titration. The last thing I want to say is that there's danger and you need to exercise concern with acids, but you also need to exercise concern with bases. And that sometimes surprises students when I talk about that, because everybody knows acids are dangerous. Think Breaking Bad, right? Walter White and Jesse, they dissolve the body in acid, right? Hydrofluoric acid or something like that. You know from working in the lab that acids can cause burns to your skin. So we know acids potentially could be dangerous. I mean, even something like lemon juice eventually erodes the enamel on your teeth if you're a person who just likes to eat lemons. However, bases are just as dangerous. So again, with the movie references, if you've seen Fight Club, they used base known as lye in their soap making. But they're also using that to burn tattoos into their skin. So you can get just as burnt, just as injured from a base than you can from an acid. So you have to exercise caution when using both in the lab. So the first step in an acid-base titration problem is to come up with a balanced equation. Sometimes they give you the equation and sometimes you have to write it from scratch. So we know we're dealing with a sulfuric acid solution, H2SO4. And we know from our solubility rules that H2SO4 is aqueous. And we're titrating that with potassium hydroxide, another aqueous species. And then here we need to figure it out what will form. So typically with the acid-base titrations, we have an Arrhenius acid and Arrhenius base, so we expect to form water. And that's what's going to happen here, because the sulfuric acid is going to break into H plus and SO4 2 minus, and then the potassium hydroxide is going to break into K plus and OH minus, and the H plus hooks up with the OH minus to form water, and then the potassium hooks up with the sulfate. Positive needs to go first, so in my head I'm doing a crisscross between K plus and SO4 2 minus, and I'm going to get potassium sulfate, K2SO4, still aqueous because it has a group 1 cation in it, right? The water, let me keep the water as HOH just for a second here, and that's going to help me with balancing. And let's see, so there's 2 potassiums, so I'm going to put a 2 out front here, and then that gives me 2 OHs. Over here, I only have 1 OH, so I'm going to put a 2 out front there. Should also designate the water as being liquid, so put that L there. And then that gives me 2 H's, which I have 2 H's here in my sulfuric acid, which is considered a diprotic acid. Coefficients of 1 there. So now we're all set with the balanced equation. Our next step then is to organize the given information. I particularly like to use a T-chart when I'm dealing with any kind of solution, stoichiometry, and the reactions. It helps me keep everything straight. The reason being, when you use the equation molarity equals moles over liters, we cannot mix and match. So what I mean by that is we can't take the molarity of our acid and the volume of our base. It's just not going to work out that way. So if you're solving this, you better have molarity of the acid, volume of the acid, and then you could solve for moles of acid. Or you could have everything in that equation be about the base. But don't mix and match the acid with the base when you use that formula. So I'm going to get organized first so I don't make that mistake. The titration of 20 mils of the sulfuric acid solution. So over here I know I have 20 mils of H2SO4 requires 22.87 mils of 0.158 molar potassium hydroxide. I'll put that information over here. To reach the equivalence point, what is the concentration of the sulfuric acid solution? So I'll just make note of that down here, that we're solving for concentration. And at least in this class, when they ask for concentration, you're looking for molarity. So again, that's why I referenced that formula. After you organize your information using the T-chart, the first question you want to ask yourself is, can I solve for moles. Moles continues to be the bridge to where we want to go. So over here, all I have is volume. I cannot solve for moles of acid. However, over here I have volume and molarity. So volume and molarity, that will enable me to solve for the moles of base. Couple quick steps then. I need to get this to liters. So I'll divide by 1,000. And then I'll use molarity equals moles over liters. So I'm going to multiply, right? In order to solve for moles, I should do liters times molarity, and that's going to give me moles. So I'm going to do 0.02287 liters times 0.158 molar. And when I did that earlier, I got 3.6, keep all these digits till the end, 3.61346 times 10 to the negative third moles. And that's going to be moles of potassium hydroxide. Because I used the volume of potassium hydroxide and the concentration of potassium hydroxide, I know I got the moles of potassium hydroxide. Once you get the moles of one thing, then you're going to go to your balanced equation to switch it to moles of another thing. And we do that by the mole to mole conversion factor. So I'm going to write this number again. So 3.61346 times 10 to the negative third moles of KOH. And then I'm trying to get rid of the moles of KOH. So I'll put that in the denominator. And the problem's asking me to solve for the concentration of the sulfuric acid. So it'd be sweet if I had the moles of sulfuric acid. I'm going to grab the coefficients of my balanced equation. So I have a 2 here and a 1 here. So that basically means in order to get the moles of sulfuric acid, I have to divide the moles of potassium hydroxide by 2. And at that point, I got 1.80673 times 10 to the negative third moles of H2SO4. Since that information is about the sulfuric acid, I can put it over here on my T-chart. Now I'm ready to solve for molarity because I have moles and I can get liters. I'll just divide this by 1,000, trying to save a tiny bit of space there. You're going to be doing a lot of just dividing by 1,000 to go from milliliters to liters. 3 sig figs. So concentration. So I'll do molarity equals moles over liters. So I'm going to take my moles of sulfuric acid that I just calculated using the mole to mole ratio. And then my volume, which we know because when you set up these titrations, you're going to measure a very specific volume. And at that point, I got a molarity for my sulfuric acid of 0.0903365, but we only have 3 sig figs. So I'm going to cut it off at 0.0903 molar. And that's the answer. Another one of these acid-base titration problems. In this one, we have potassium hydroxide and hydrobromic acid. So the first thing I'm going to do is write a balanced equation. I know that both of these species are aqueous. And when we do titrations, we typically deal with aqueous solutions. But it's always nice to think about our solubility rules and make sure that it still applies. This one's not too bad. We know that this is going to do K plus and OH minus when it dissociates. And here we're going to have H plus and Br minus upon dissociation. So we're going to get water and potassium bromide as our products. The water is going to be an L after that, and for liquid, and potassium bromide would be aqueous. It'd be mixed in and dissociated in the solution. Next step, I already have my T chart here. I'm going to organize my information. So the molarity of an aqueous solution of potassium hydroxide is determined by titration against a 0.138 molar hydrobromic acid solution. So I'm going to put that information on the acid side of my T chart. 27.4 mils of the base. So I know that potassium hydroxide is my base because it's an OH minus and a hydroxide ion producer. So I'm going to put that piece of information over here. And because eventually we're going to be using the molarity equals moles over liters equation, let me just go ahead and divide this by 1,000. I'm going to get 0.0274 liters. And then that volume's set to go already. Okay, so 27.4 mils of the base is required to neutralize 21.6 mils of the hydrobromic acid. So now we have another volume. I'll put it on the acid side. I'll divide by 1,000. So 0.0216 liters. What is the molarity of the potassium hydroxide solution? So over here we're solving for the concentration of our base. So again, after we organize everything, after we have a balanced equation, the next question we have to ask ourselves is, do we have enough information either on the base side or the acid side to solve for moles? Over here I just have volume, so that's not going to help me. Over here I have concentration and volume. I know I can multiply those two and get moles. So let me set up that part. I'll do 0.138 molar times 0.0216 liters equals 2.9808 times 10 to the negative third moles of hydrobromic acid. Eventually you'll be able to work these problems a little bit quicker. One thing that I'm recognizing from this equation, because it's balanced as is, it's a 1 to 1 to 1 to 1 ratio. So that tells me, and I'm going to set it up both ways, but so that you can start gaining speed. That tells me, since everybody's 1 to 1 in that equation, all the coefficients are 1, that the moles of acid is equal to the moles of base. So over here, I know I'm going to have 2.9808 times 10 to the negative third moles of the potassium hydroxide. However, if you want to be 100% sure, or you want to see how that works, right, we can write the hydrobromic acid, because that's the one we were able to solve for with the given information. Try to get rid of moles of hydrobromic acid. Turn it into moles of potassium hydroxide. And I'm going to fill in the fact that they're 1 to 1. So with the 1 to 1 coming from the coefficients of the balanced equation. Almost done. And another thing you'll notice, there's no molar masses in these problems. We're typically not using the scale. We're going to see a couple of exceptions in next week's lecture. Molarity equals moles over liters. So for the molarity of the potassium hydroxide, I got 0.1087883, but with rounding and everything, I'm going to report it as 0.109 molar because I only have 3 significants. Alrighty, so another titration problem. This one's a little bit different in that we don't have an Arrhenius base. We have baking soda, sodium bicarbonate, and that's going to be the base in this problem. Eventually you'll learn how to recognize that, but for now I would say if you come across a compound and you're uncertain as to whether it acts as an acid or base, just Google it, because some of them are hard to recognize. Sulfuric acid, though, we know that since it produces the H+, this is going to be our acid. So somebody mixed H2SO4 with baking soda, sodium bicarbonate. We need to predict the products of this reaction. So as I always do, I'm going to split this into ions. So I'm going to do H+ over here and SO4 2- over here. I know carbonate is an ion on its own, but we have to be really careful. Typically, you only want to split up our compounds into two distinct ions. So I'm going to take the metal part, the metal ion, and then I'm going to keep this as hydrogen carbonate or bicarbonate. Now I'm going to do-si-do it that way. So this H+ then is going to hook up with the bicarbonate, the hydrogen carbonate, and then we have sodium hooking up with sulfate. Reorder this, do your crisscross. You're going to get Na2SO4. And this one, you could think of it as a crisscross, right? We have a +1 and a -1. But instead of having just one hydrogen, we're going to have two hydrogens. So this is going to form carbonic acid when we crisscross or combine those. Let's balance this equation. So I have two sodiums over here. So I'm going to throw 2 out front here, which gives me 2 carbonates, and I can see that right there. And so over here I only have 1 carbonate. So if I put a 2 out front, that helps that problem. Over here now I have 2 hydrogens and 2 more hydrogens for a total of 4 hydrogens on this side. And 2 times 2 is 4, so I have 4 hydrogens on that side. So it's balanced with a 1, 2, 1, 2. Now we put like some brakes or something. I need some sound effects here. You're going to say, but I've mixed an acid. Maybe you mixed vinegar with baking soda. Classic volcano experiment, right? Like, I saw a lot of bubbles. I saw a gas being formed, and you're absolutely right. If you mix sodium bicarbonate with any kind of acid, you will see the production of a gas. So let's talk about that super quickly before we jump into the math. This carbonic acid, it's the same acid that's in soda. The carbonic acid continues on to a second reaction. And it happens so quickly when you do that volcano experiment, or if you were to do this combination, that you don't even realize, oh, it's one reaction. Bam, a second reaction happened. So the bicarbonate, the carbonic acid is going to decompose into carbon dioxide, which is a gas, and water. So now we can justify a couple things. We can justify the bubbles that we see when we do reactions with baking soda. That's going to be carbon dioxide bubbles, the same gas that you breathe out. And we can also justify the fact that we can use phenolphthalein as our indicator. We do have a neutralization occurring. It just takes several steps to see the production of that water. Our coefficients, however, the ones that we're going to use, we're going to focus on this top equation when we're considering the math here, because both of the species they ask us about or give us information about, the baking soda and the sulfuric acid, are present in the top reaction. So I'm going to really focus up there. A student finds that 37.80 mils of 0.4052 molar sodium bicarbonate. So let me put that over here. 37.80 mils. I'm going to divide by 1,000 and get that in liters right off the bat. And they gave me a concentration of that as well. Required to titrate 20 liters. Now 20 liters of sulfuric acid. It's a lot of sulfuric acid, but we'll go with it. How to do a double take there. Usually we're in mils, right? What is the molarity of the sulfuric acid? All right, so I'm going to approach this the same way. I ask myself, do I have enough information to solve for moles? Well, definitely on this side, with the volume and the molarity, I can use those two values to solve for moles. So I'm going to do 0.03780 liters times 0.4052 molar, and that gives me 1.531656 times 10 to the negative 2 moles of sodium bicarbonate. When we're going from moles of one thing to moles of another, we need to use the coefficients of our balanced equation. All right, so I'm going to use this number, and I'm going to rewrite it over here so I can convert the moles of my base to acid. So I'm trying to get rid of the sodium bicarbonate. So that's going to go in my denominator. I want to turn it into moles of sulfuric acid. So I'll put that in my numerator. There's a 1 associated with the sulfuric acid. I'm focusing on the top equation. And a 2 with the sodium bicarbonate. So when I divided that, I got 7.65828 times 10 to the negative 3rd moles of sulfuric acid. Now I can take that number and put it in the acid side of my T-chart. The last step then is to solve for the molarity. So it's going to be moles of the acid divided by volume. So I'm going to have that same value. And it's going to be divided, I'm going to divide it by 20. At the end of the day, I get a molarity of 3.83 My calculator says 3.82914, but I only have 3 sig figs. So I'm going to report it as 3.83 times 10 to the negative 4 molar sulfuric acid. In the back of my head, I keep on thinking, in what world is somebody titrating 20 liters? And I should update this problem to make it a little bit more realistic, because we do use baking soda solutions. They're in the lab. You might have seen them just like by the hoods, on top of the hoods, in kind of white Nalgene bottles. We do use baking soda solutions to neutralize acid spills. So it would make more sense in my mind if somebody spilled 20 liters of sulfuric acid and they really had no idea how concentrated it was, but it only took about 37, 40, 38 mils to neutralize that spill, because that's the approach you would take if you spilled an acid in a lab. You'd start putting a baking soda solution on it. Anyways, at the end of the day, the value that you want to report as your answer is this 3.83 times 10 to the negative 4 molar sulfuric acid.